in the beginning was Landsat. So actually, originally the Earth Resources Technology Satellite, following NASA's penchant for naming Earth observing systems wonderfully. Launched in 1972. This is possibly first light. In any case, it's the first image that's, or the earliest image that's in the archive from the ARIS data center. Landsat 1 carried 2 instruments, the return beam Videocon, which was never actually used, and the multispectral scanner, which was sort of an add-on instrument, which nobody thought would work and ended up being the heritage sensor that basically everything since has followed on. And it's a 4-band sensor. There was a near-infrared, a not quite infrared, not quite red, red and green. Interestingly, not square, so 68 meters by 83 meter resolution. And that was originally launched in 1972 in the summer. And since then, the Landsat program has continued without real interruption since then, even though one Landsat 6 never made it to orbit. This is the Landsat archive from 2000 to 2015, where you can see the enormous amount of data that's been provided here. Currently, Landsat 8 has improved, the spectral quality has improved dynamic range, bit depth, number of bands, resolution, everything. We have also, since the mid-'80s, commercial remote sensing has started happening. Landsat took a short foray into that. But really, the beginnings of that was with SPOT in 1986, launched by the French CNES. And similar to Landsat, it was a near-infrared, red and green, higher resolution, 20 meters per pixel with a 10 meter per pixel panchromatic band. And then in the very last stages of the 20th century, we started getting high-resolution commercial satellites. The first of which was IKONOS 2, the first one to reach orbit. Originally space imaging, then GeoEye, then Digital Globe, now Maxar. So there's a long history of acquisitions there, acquisitions and mergers. And this is an image that's actually in the USGS archive, where there's a collection of IKONOS data of Alaska, which is kind of fun to download and play with. This is the Tuxedni River, and it is their 1 meter per pixel panchromatic RGB combined with their panchromatic band. It's the panchromatic, which is 0.4 to 0.9 micrometers, plus the 4 meter per pixel RGB, blue, green, and red. One thing to note is with some of these early very high resolution sensors and also Landsat 7, the panchromatic band incorporates a lot of near infrared light. And so it's not necessarily accurate in places like forests where they're very reflective in the near infrared, very absorptive in visible. And so you get kind of this washed out gray appearance. And that is one of the things that's actually very important for multi-sensor comparisons. Now the state of the art is WorldView 3, WorldView 4, both Digital Globe / Maxar. I don't even really know which is the appropriate attribution to give at this point. They're up to 0.3 meters per pixel. WorldView 3 also has some shortwave bands, but this is a picture of Bondi Beach at WorldView 4, and you can get down to the resolution of individual towels on the beach. So while the commercial world was going towards higher and higher resolution, there was also a parallel track of public remote sensing systems that were going towards higher and higher frequency. And so sort of the beginning of the heritage for that line of sensors was the advanced very high resolution radiometer, launched in 1978. Obviously, our definition of very high resolution has changed in the intervening 40 years. But this is, I thought this was very cool, digging into the AVHRR archive, a 2-year composite of the United States made from infrared, near infrared, and panchromatic information. And so some of the earliest large-scale mosaics. And now the state of the art is VIIRS and OCLI from the ESA. And we're getting daily multispectral coverage in visible near-infrared, shortwave infrared, and thermal infrared of the entire globe. And so this is some of the early VIIRS imagery January 18th to July 25th in 2014, showing the really great temporal resolution that we get. So I work for Planet, and in some ways our main constellation, which is the PLANETSCOPEs, fits in between the very high temporal resolution of public sector satellites and the very high spatial resolution of some of the commercial constellations that are out there. And we actually have 3 different classes of satellites. One is RapidEye. They're medium resolution with a long-term archive. The Dove/PlanetScope constellations, which are the CubeSats with which we do daily observations of the entire Earth at 5-ish meters per pixel. And then 13 SkySats, which do tasked observations at 0.8 meters per pixel. And then here is just an overview of some of the more technical aspects. And here's how we fit into the larger ecosystem of remote sensing. You go from, in cadence, a task cadence, which can be variable. Worldview 3, Worldview 4 actually are very agile, have a lot of onboard storage, and they can get daily or near daily observations if you request it. But as a global average, it's much lower than that. And then moving to the right, you're going towards the 2-week and weekly cadence of Landsat 8 and Sentinel, and then the daily cadence of VIIRS, MODIS, and their class of instruments. And then PlanetScope is sort of off that axis, where you're getting moderately high resolution at a very high cadence. So here's an example of what I think is most valuable about the RapidEye archive, and that's that it gives us a history, which you can then look at the more recent data from PlanetScope. This is the Salar de Uyuni in Bolivia. It's a lithium mine on the largest salt flat in the world. And then 2011, this was virtually pristine. 2012, you start seeing the first hints of the infrastructure being developed, and then the mine nearing full operation last year. SkySat, on the other hand, provides pinpoint accuracy. And so 0.8 meter per pixel panchromatic, 1.2 meter per pixel multispectral, 13 satellites. Because it's tasked like Digital Globe, it'll be sort of a variable cadence. But this is the Reading fire from Sunday morning, showing individual houses that have burned versus individual houses that survived in one of the big wildfires that's been occurring in California. And then PlanetScope, which I mentioned, has a near daily cadence. And this is what it looks like when you looked at fields that turn over very rapidly near Salinas. This is probably lettuce or other crops that really don't take very long to grow at all. And so you can see this very fine-grained change, both spatially and temporally. And so one of the really interesting applications for this is not looking at it as a series of slices, but actually starting to use the time as a completely new dimension. And so we're taking NDVI for individual plots, plotting them over time with each observation. And this is actually a fairly trivial example, but it's also really powerful, where we're actually differentiating soybean from corn at the actual parcel level before the official government reports are released that give acreage in certain areas by the US government. And so this is really what I'm most excited about with high cadence, is really starting to look at new ways of using the data that really weren't possible with either weekly or the sporadic types of cadence that you get with the tasking. Of course, it's not that simple. We took some shortcuts to do a constellation of over 100 satellites. They're small, so the resolution is definitely capped at 3.9 meter ground sampling distance. We use a commercial camera with a color filter array, which means that we're not sampling RGMB for every pixel. And so we're interpolating on a kernel, and so you get cross-contamination from adjacent pixels. Bad pixels will destroy more than just one, et cetera, et cetera. Also, because we're using a commercial camera, we don't have nice narrow bands. And so there's some overlap, and that needs to be pulled out. And also, commercial cameras, generally speaking, don't have an IR channel. And our solution to that was to switch to a 2-band where we leave the bare mask intact, but we pull off the IR cut filter that's typically applied in a commercial sensor, and then put on a tube stripe sensor or a filter, one of which is IR cut and one of which is visible cut. And then we have to recombine those into RGB data or near-infrared, red, green, blue, the 4 bands that we have. So this is Menlo Park from late July with the 3 different frames, and then combined into a full RGB image. One of the other limitations that we have using the commercial sensor is the dynamic range is impacted. And so you'll notice that some of these salt flats are blown out and saturated. And what we're trying to do is actually move from the more traditional delivery of pixels, which I guess would be the type of thing that the customer base that wants analysis-ready data is typically consuming, into what was termed earlier here customer-ready data. We actually usually call it analytics. And so a derived product. So we're not just delivering an image or a geodata set. We're actually providing like vector boundaries or closer to the actual information that the customer wants. And so one example of that is doing deforestation detections in Brazil. So this is 2017. And this is actually weekly detections, everything above 1 hectare from July through the end of December. Also looking at buildings and roads. So this is an internally displaced persons camp in Syria, one of the world's worst euphemisms because they're not refugees if they don't cross an international border. But from June 2017 to October, November of 2017, you see the infrastructure start to develop, beginning with roads. And then the individual housing units get put in. And so this is detected automatically by algorithm. And then, again, is an example of one of our analytic products. So thank you very much. This is where you can get in touch with me, and I'll be happy to answer any questions. So the question was, how early do we do the crop classification? That's not a product yet, so that was a demo. That data, depending on how many observations you think you need to make that determination, would have come in anywhere from a month to 2 weeks before the official report.
So I've been a planning user for a little while, and one of the things I try to harp on every time I talk to somebody is, do you have any plans for collecting large-scale off-nadir data? There's a lot of value in off-nadir rather than just nadirless, and the archive is very, very small in off-nadir.
Right. So the question is, do we have plans to do off-nadir imaging? Is that for PLANETSCOPE or is that for SkySat or either?
For PLANETSCOPE.
Right now, no. I'm assuming if there was a compelling enough business case that we'd revisit that. But right now, it's definitely nadir, near-nadir operations.
So appreciate the walk down memory lane, the history. That's great. One item I would have expected maybe was MODIS, which you didn't mention. It was on one of your graphs. And I haven't heard MODIS talked about at all in the last day and a half, I think. Is there any reason for that? In your mind, why didn't you put MODIS in your talk?
The question is, why no MODIS? I considered it. Basically, I didn't think it was necessary as, well, it's definitely an important step going from AVHRR and in some ways remains the state of the art. I just didn't want to belabor the point of having VIIRS and OCLI and MODIS and MERIS. There's too many. No, we use MODIS for atmospheric correction. We absolutely use MODIS. And I used to be part of the MODIS science team, so it's certainly an instrument that's near and dear to my heart. But it's just, it wasn't the focus of the talk, that's all. No, it's a fantastic instrument. Luckily, they've decided to keep Terra and Aqua in orbit for a long time still. And they are absolutely essential to this entire endeavor.
thank you, Rob, again.